today we're wanting some additional support on how to graph Newton's second law, part 3 of the lab. In Newton's second law, part 3, we were using a cart string hanger setup with a frictionless track, massless, and frictionless pulley. We're assuming the string is massless, and we have a hanger down here. And the big question that we're trying to answer here is, while maintaining a constant net force, how does increasing the mass of the system affect the overall acceleration of the system? In order to keep the net force constant, we're not going to change the mass of the hanger. The mass of the hanger in this example is 35 grams or 0.035 kilograms. What are we changing this time? The mass of the system. How are we going to do that? Well, we're going to go ahead and run a trial with the cart string and hanger and measure the acceleration using the slope of the velocity versus time graph with the N2 smart pulley program. After the 3 trials of that, you're going to take and grab one of these extra bars, maybe, and put it on the cart. And that adds 50 grams. And then you can go ahead and run 3 more trials of that, measuring the acceleration after each trial. And you'll continue to add more bars to the cart and so on. So after you have collected all of these masses of the system, and to calculate the mass of the system, you take the mass of the cart string and hanger and add whatever additional masses to it. And you've also recorded the accelerations along the way. Now, what does that look like for graphing? Well, here's the sample. Again, the mass of the cart string and hanger was 200 grams or 0.200 kilograms. The additional mass bars were 50 grams apiece or 0.050 kilograms, and we were pretending that the mass of the hanger is 35 grams or 0.035 kilograms. So total mass of the systems I've put in this column. Make sure that you have the name and the units at the title and only values here, and then you'll put your accelerations. I do want to keep in mind you are not supposed to be using these values. These values won't match any of the setups that we use during class or the other videos I've sent out. This is simply the process you want to follow through. Now that you've got a title and values for these 2 columns, we have our independent variable in the first column and our dependent variable acceleration in the second. You can highlight these 2 columns and just choose insert a chart, either using this icon or go to insert and choose chart. After doing that, you're going to have a graph show up. If you get lines on the graph instead of these points or scatter chart, the way you can move that around is go up to setup. And under here, you can choose the different kinds of graph. We don't want a line, actually. We want the scatter chart that showed up there initially. And the overall shape of that will be a little bit easier to see if we zero out this x-axis. So I clicked on the values of the x-axis, and I'm going to type in 0 here. That's a little crazy there. But is this more like a line or a curve? That's actually kind of tough to see that way. But if we take a look at this, we'd find out that that's actually a curve. Now, how do we go about linearizing that? So to linearize that, mathematicians and scientists have said, since this is mass of the system increases, the acceleration is decreasing, we say that these variables are inversely proportional. As the mass got bigger, the acceleration got smaller. Well, how do you linearize that? Well, to linearize that, we're going to have to manipulate the x-axis. We're going to have to manipulate the mass of the system. To do that, we're going to have to make a new column, and we're going to have to call it 1 divided by the mass of the system. The units for that are going to be 1 divided by kilograms. So you can either pull out a calculator and do 1 and divide by this value and put it in, and 1 divided by this value and punch it in, or we can teach the computer how to do it. To teach the computer, you click in the cell below the title and type in equals, and that's saying, hey, I want you to calculate the following thing. You type in the number 1, the forward slash, I don't know what happened there, the forward slash, try that again, 1 forward slash, and then you're just going to click on the cell that's underneath the name of the mass of the system, right here where it says 0.2. And notice that column C2 pops up in there, and hit enter. When you do that, you might get this screen that says suggested autofill, and you go ahead and select that and it'll fill those in. If you didn't do that, if you didn't do autofill, the other thing you could do is, see this blue box here? grab that and just drag it down, and it's going to apply that formula to each of these. So it's now taken these mass of the systems and calculated 1 divided by the mass of the system. 0.2 is 1/5, so 1/5 turned upside down is 5. 0.25, 1/4, turn that upside down, it's 4, and so on. Because we're going to want to make an acceleration versus 1 over the mass of the system graph, this computer works better if you just have what's in the x-axis listed first. So we're going to copy the average acceleration and throw those over there. And now we've got the x-axis in this column, the y-axis over here. We're going to go ahead and highlight those 2 columns. And again, you can hit chart, insert chart here, or go up to insert and choose chart. Now when we lay this out, we're going to squish this down a little bit, make it a little smaller. First, you want to double check and make sure that things are on the right axis. You have acceleration on the y-axis and 1 over the mass of the system here. And because we included the units in the title cell, the units show up there, and the title on the graph is correct as well. And is this a line or a curve? This is a line. So to analyze this, we're going to have to do something a little different. Over here in the chart editor, and to get that to show up, if for some reason the chart editor doesn't pop up, if you just click on the graph or double click on the graph, that'll pop up. You can go over here to customize. Within there, you want to find series. Opening series, you're going to find a trend line, which is like the best fit line we drew with the ruler at the beginning of the year, and that lines up pretty well. Looks like we have 1 data point that's a little off, so we might want to take a peek at that later. Once we have the trend line, go down about 3 rows and ask for label. And as we've done before with these sheets, you want to say use equation, and an equation will pop up here. Now the equation is in the format of y equals mx plus b. So the name of the y-axis is acceleration. The slope is 0.33. It doesn't include the units, but you have to assume those, since its rise over run would be meters per second squared per 1 over kilogram. Then it says times x. The name of our x-axis is 1 over the mass of the system. All right, and the y-intercept is 0.0752. Now, if we zero this out, we should end up with a y-intercept that is pretty darn close to 0. So I'm going to go ahead and click on the x-axis values. This pops up under the horizontal axis. I'm going to put 0 in here, and you can see that the y-intercept would be pretty close to 0 down there. At this time, I'm going to shrink this graph down so that it fits the space a little bit better. Scooch it out of the way of the other graph. And maybe we can make this one a little smaller so it can all fit in the screen at the same time. So now we have on here mass of the system, the average acceleration, 1 over the mass of the system, the same accelerations from column 2. And again, you just highlighted E and F to make the acceleration versus 1 over the mass of the system graph. This y equals mx plus b over here, this specific mathematical model, is what you're going to use for your mathematical analysis. And you'll find through our other discussions that the slope of this graph should be reasonably close to the net force acting on your system. I hope that helps.